Work is done when a force moves a body through a distance. Consider two forces F and W acting on a body. Consider two forces F and W acting on a body, one horizontal and the other vertical. Now, due to these forces, the body has covered a horizontal distance. Since the direction of displacement is parallel to F, the work done by the force F is F times d. Since the direction of displacement is perpendicular to W, the work done by W is 0. Work is done only when the body moves in the direction of the force. Consider a waiter holding the tray and moving horizontally with a tray in this hand. The waiter's hand is exerting an upward force on the tray. Now, the force exerted by the waiter's hand on the tray does not do any work as the waiter moves horizontally, since it is perpendicular to the direction of motion. The work done when you move down a slide is your weight times the vertical height covered. Your weight is the force acting downwards, and remember, it has to be multiplied by the displacement in the same direction as the force. Do not make the mistake of multiplying the downward force with the length of the slide. Always remember that force and displacement have to be parallel, and their product yields the work done. When you move heavy objects into a truck, you normally use a ramp. When the ramp is very steep, you have to move a shorter distance, but you have to apply a greater force. When the ramp has a gentle slope, you apply a lesser force but over a larger distance. You can try these cases by moving the slider to adjust the ramp position. In both cases though, you will end up doing the same amount of work. Consider a ramp at an angle theta. There is a block of mass m placed on the ramp. The weight of the ramp acts vertically downwards and is mass times gravity, mg. This force can be resolved into two components, one parallel to the ramp and one perpendicular to the ramp. The component of force perpendicular to the ramp is mg cos theta, and the component parallel to the ramp is mg sin theta. Consider an external force acting on a block placed on an incline. If the direction of the external force is parallel to the ground, it can be broken into its two components, one parallel to the incline and the other perpendicular to the incline. The one parallel to the incline is f cos theta, and the one perpendicular to the incline is f sin theta. Let us assume a block sliding down the incline, and we need to find out the work done by the gravitational force. Now notice that the gravitational force acts downwards, and the displacement of the block is not parallel to it. So, we resolve the gravitational force into its two components, one parallel to the incline and the other perpendicular to the incline. The component of the force perpendicular to the incline, mg sine theta, is now in the same direction as the displacement L. The work done, therefore, is mg sine theta times L. Let us look at another way of solving the problem of computing the work done by the gravitational force as the block slides down the incline. Here, we will not resolve the gravitational force, but keep it in the same direction. We will instead find out the distance it covers in the vertical direction, which is L times sine theta. The work done by the gravitational force is therefore mg times L sine theta. This is the same work done as in the earlier case. There we resolved the force and took the distance as the actual distance the block travelled. Here, we need to compute the work done by an external force in moving the block up the incline. Here, we will resolve the force into the two components, and the work done will be the component of the force parallel to the ramp times the length of the ramp, as both will be in the same direction. The work done is F cos theta times L. We can compute the work done by an external force in moving the block up the incline in another way. We will not resolve F, but instead find the distance travelled parallel to F. So the work done is the F times L cos theta, which is the same as the work done in the earlier method of resolving the forces. When an object moves in a circular path, a centripetal force acts on it, which points to the center. The displacement is at a tangent to the circle, so it is perpendicular to the centripetal force. Now, since the force and displacement are perpendicular, the work done is zero. Gravitational potential energy is the energy stored by a body on account of its height. It is directly proportional to the mass and to the height. Gravitational potential energy is mgh. Compression potential energy is the energy stored by a spring on account of its stiffness and compression. The compression potential energy is directly proportional to the spring stiffness and compression. The gravitational potential energy increases when the swing is at a high position and decreases when the swing is at a low position. At the highest position of the swing, the potential energy is at the maximum, which would be at the extremes. At the lowest position of the swing, the potential energy is at the minimum, which would be at the midpoint. Think of two blocks being raised, one along the incline and the other straight up. When they reach the top, both blocks would have the same potential energy mgh. So, if a block is raised to a certain height, the path taken to raise it will not matter. It will contain the same potential energy at that height, regardless of the path. Kinetic energy is the energy possessed by a body on account of its mass and speed. Kinetic energy is directly proportional to the mass and to the square of the velocity. If the velocity is doubled, the kinetic energy increases by a factor of 4. The velocity of a swing is the maximum when the swing is at the center and 0 when the swing is at the extremes. At the highest position of the swing, the kinetic energy is 0, and at the midpoint of the swing path or at the lowest position of the swing, the kinetic energy is the maximum. Imagine you were moving in a car and had to suddenly apply the brakes. Let's say you were driving at 30 kilometers per hour and after braking the car stopped 1 meter from the point of braking. At the extremes, the kinetic energy is 0 and the potential energy is at its maximum. At the midpoint of the path of the swing, the potential energy is at its minimum and the kinetic energy is at its maximum. In between, the swing has both kinetic and potential energy. Imagine you were moving in a car and had to suddenly apply the brakes. Let's say you were driving at 30 kilometers per hour and after braking the car stopped 1 meter from the point of braking. If, let us say, you were driving at twice the speed, 60 km per hour, if you apply the brakes with the same force, you would come to a stop 4 meters from the point of braking. By the law of conservation of energy, energy is neither gained nor lost, but converted from one form to another. In the swing, the loss in potential energy from the extremes to the mean is the gain in kinetic energy. The loss in kinetic energy from the mean to the extremes is the gain in potential energy. Consider a ball moving the same distance vertically in 4 different ways. They have the same potential energy to begin with, since they are raised the same height from the ground. By the law of conservation of energy, they will have the same kinetic energy at the bottom, since their potential energies must have got completely converted to kinetic energy at the bottommost point. Kinetic energy is proportional to mass and the square of velocity. The mass is identical in all 4 cases, which would mean that the velocity would also be identical at the bottom. When the pendulum is released, it has only potential energy. So, by the law of conservation of energy, it will come back to the same height and point. If it is given a push besides the potential energy, an additional energy is imparted to it. So, it will rise higher in its swing, since the potential energy at the extreme must be the addition of the original potential energy plus the energy due to the push. In the first case, the level is flat, so the ball continues with the same speed. In the second case, there is a drop through which the ball travels. When the ball gets into the drop, it loses some part of its potential energy, which gets converted to kinetic energy. But when it climbs out of the drop, it gains the same amount of potential energy and loses the gained kinetic energy. So, it exits the drop with exactly the same speed with which it entered the drop. Whether a nail is inserted or not, the law of conservation of energy will still hold. The pendulum will rise to the same height because the potential energy with which it started at the left extreme must be the same at the right extreme. Note that the kinetic energies are zero at the extremes. We are given a large truck with a low velocity and a small truck with a larger velocity, such that their momentums are the same. We have to determine which one has the higher kinetic energy. Kinetic energy is half mv squared, which can also be equivalent to half momentum times velocity. Since the momentum is the same in both, the truck with the lower velocity will have the lower kinetic energy. Here, we are given two trucks with the same kinetic energy, but we have to find out which one has a higher momentum. Kinetic energy can be expressed as half momentum times velocity. It is clear that for the same kinetic energy, the truck with the lower velocity will have a higher momentum. The momentums of the two skaters are the same. The energy imparted on the standing person will be half momentum times velocity. So clearly, the skater with the higher velocity will have higher kinetic energy and will cause more damage than the heavier skater with lower velocity. When the ball in the second case goes through the drop, due to the decrease in potential energy, its kinetic energy increases, and therefore its velocity increases, and it covers the distance between x1 and x2 faster than the ball on the flat track. Ultimately, they reach the finish with the same velocity, but the ball that goes through the drop reaches first. Power is the work done in unit time. If you do the same amount of work, you have a higher power if you do it in a lesser amount of time. By using the slider bar, you will notice that the forklift does the same amount of work, but when it takes 2 seconds to do it, its power is greater. Both the forklifts have done the same amount of work as they have moved an equal load by the same distance. But the red one has done it in half the time and is therefore twice as powerful as the yellow one. A horsepower is another unit of measuring power. A horsepower is approximately 750 watts. Here you can see that the red forklift has twice the horsepower of the yellow forklift and hence can perform the same amount of work in half the time. Renewable energy is energy that is continuously replenished as it gets used. Examples are solar energy, wind energy, and hydro energy. Renewable energy is extremely important as it provides environmental benefits over conventional energy technologies. Renewable energy is energy that is continuously replenished as it gets used. Examples are solar energy, wind energy, and hydro energy. Renewable energy is extremely important as it provides environmental benefits over conventional energy technologies. Since they are continuously replenished, we do not have to worry about running out of resources. Geothermal energy uses the heat of the earth to warm buildings on cold days. Hot water runs through piping around the building, keeping it warm. The heat of the earth can also be used for cooking and bathing in hot springs. When a neutron collides with a uranium nucleus, the nucleus splits into two smaller atoms and releases a large amount of energy. This replaces the burning of coal or gas and thus reduces greenhouse gases. These reactors are used to generate cheap electricity. On the other hand, nuclear accidents can cause great harm to humans.
Solar cells have low running costs and are environmentally friendly. But the initial cost of the panels is very high.
Windmills use wind energy, which again is renewable. The wind hits the blades and turns them. The blades are connected to an armature between magnets. The blades rotate the armature between the magnets, which generates electricity. The disadvantage is the dependence on the wind. Hydroelectric power is generated by using flowing water to turn the blades of a turbine. The turbine blades are connected to an armature, which is housed between magnets. As the armature rotates between the magnets, electricity is produced. Normally, this is done on a large scale using dams. The disadvantages are the high cost and destruction of the land around due to flooding, as well as the displacement of people living around. Non-renewable sources of energy are those which will get scarce as time goes on. Non-renewable energy comes from fossil fuels like crude oil, which were formed from dead sea plants and organisms millions of years ago. Petroleum is obtained from the earth by drilling. We have learnt that in any process, energy gets converted from one form into another. Consider the lighting of a bulb. The electrical energy input into a bulb theoretically gets converted into light energy, which is useful to us. But in the process, part of the electric energy gets converted into heat energy, which is not useful to us and is lost energy. The creation of non-useful energy results in degradation of energy. The heat energy generated by fission is used to heat cold water until it turns to steam. The steam turns the turbine blades, which are connected to an armature housed between magnets. As the armature rotates between magnets, electricity is produced.